8.1 vector and parametric equations of a line in R squared. Okay, so we're going to look at equations of a line, but they're going to look a little different this time. Okay, they're going to no longer be in y equals mx plus b, but we're going to express them as vectors. Okay, and this is all going to be in R squared, so just 2D, so x comma y. Okay, so vector equations of a line in R squared. It's going to be denoted by R, like vector R. Okay, and then we have R naught so vector R naught, and then some parameter t, and m is going to be a direction vector. Okay, so R naught is a vector from 0, 0 to the point xy, and vector m is going to be the direction vector with components a, b. Okay, so direction vector. Okay, this is what we need to form a vector equation. We need two distinct points, or we need one point in a direction vector. Okay, this is the reason. Pretty much we're putting in a point and we're putting in a direction vector, but if we have 2 points, we can just find or calculate the direction vector. Now, parametric equations. We're going to be able to switch back and forth between vector and parametric. Parametric equations are specifically each component individually. So we have x equals and then y equals, and then eventually we're going to get into z equals. Okay? We're going to take the vector equation and we're going to break up. X naught and y naught are going to be just some point. So for example, if the point's 1, 2, the x naught would be 1 and then the y naught would be 2. Okay, we still have some parameter t. And then we have a, b. So again, those are the components. A, b are just the components of the direction vector. So it's pretty much taking the vector equation and just splitting it up into everything that has to do with the x's and then everything that has to do with the y's. Okay, when we say parameter, okay, so t is a parameter. T can be replaced by any number in order to get any duplicate or any... We say it's kind of similar to applying the slope. So y equals mx plus b. If you had this equation, remember on the Cartesian plane, we would be able to sub in any x and get like the next point on the line. Okay, that's very similar to this parameter t. If we sub in the same parameter t for both the parametric equations for x and y, we're going to be able to find another point on that line. Okay, for this one, again, we need either 2 distinct points or a point in a direction vector. Okay, here's a little bit of a recall. A direction vector is a non-zero vector. We call it direction vector m. Okay, AB, it's parallel or collinear to the given line. Okay, given line. And it's represented with its tail at the origin and then its head at the point AB. So wherever it is located, we just pick it up and we relocate it to 0, 0. Okay, the A and the B of the direction vector are called the direction numbers. And please note, the direction vector may be multiplied by a constant to ensure that both direction numbers are integers. Okay, so direction vectors need integers. For example, if we had like 1/2 and we had 1/3, we could multiply this by 6, which is like the lowest common multiple, and we would get 3, 2. Right? 3, 2. Oops. Saying 6. Okay, and then these two again would be equivalent. Just like 1, 2. If you multiplied it by -1, it would become -1, -2, again equivalent. Example 1, a line passing through point 4, 3 has vector m equals -7, 1 as its direction vector. Sketch this line. Okay, so if we were to plot the point 4, 3, that's no problem. 4, 3 goes right here. Okay, and that's point P. Now, if we think about a direction vector, -7, 1, I would first plot that as a vector, centered at the origin. So all we would want to do is we would want to pick up this direction vector and have our line go at the same angle, the same slope as it, pretty much. Okay, so if I were to start at P, I would apply what we're doing right here is we're relocating this origin at P. So I would go -7, 1, 2, 3, 4, 5, 6, 7, and then +1. And I would have like the head of my vector as shown. Okay, and you can keep going in both ways. Okay, a line passes through the points A, 1/2, -3, and B, 3/4, 1/2. Determine a direction vector for this line and write it using integer components. Okay, so for part B of this question, so this is A, this is actually like applying a direction vector in a graph. For part B, what we want to do is we actually want to find the vector, the direction vector. Okay, so we're going to do this algebraically. So we're going to find vector AB. Okay, AB. And what we want to do when we find vector AB is we want to do the coordinates of B minus the coordinate of A. So I'm going to do 3/4 minus 1/2 for the x's. 3/4 minus 1/2. And then I'm going to do a comma, okay? Because we're still going to have it in component form. We're going to have it x, y, okay? Or in this case, because it's a direction vector, we're going to have it in A, B. Okay? Now we're going to go 1/2 minus -3. 1/2 minus -3. Okay, so now all we have to do is calculate what is 3/4 minus 1/2. I get 1/4, and 1/2 plus 3. So for this, I get 1/4, comma, I get 7/2. Now, this is the direction vector. We don't want the direction vector to have any fractions. So what we're going to do is we're going to multiply this by, I call it the lowest common multiple. You might remember that from grade 9. So I know if I multiply both of these by 4, it's also going to cancel out that 2. So 4 times 1/4 is going to equal 1. And then 4 divided by 2 is 2. So we get 14 for that. Okay, that means AB is the direction vector, and it's equal to 1, 14. We can also write this as vector M equals 1, 14, or you can do the -1, -14, and that's still okay. Determine the vector and parametric equations of a line passing through the point A, 1, 4, with direction vector M, -3, 3. So first, vector equation. Okay, so we go vector R equals, what we want to put in here is the point, 1, 4. Then we want to put plus the parameter times the direction vector, -3, 3. Okay, now for parametric. What we're trying to do is we're trying to separate the x and the y components and everything that goes with them. So the x in 1, 4 is 1. And the x, or the a value in this direction vector, is -3. So we put 1, and instead of plus, we would put -3t. -3t. Now the same for the y. In 1, 4, the 4 is the y component, and then we have plus 3t. And there are our vector and parametric equations. Now we're going to sketch the line and determine the coordinates of 4 points on the line. So I can start at the point 1, 4. 1, 4 is right here. And then what we're going to do is we are going to apply -3 in the x direction and 3 in the y direction. -3 in the x direction, 3 in the y direction. -3 in the x direction, 3 in the y direction. Then I'm going to be off my graph. So what I'm going to do is switch this. So if we had vector m and I had -3, 3, what I'm going to do is I'm going to multiply this by -1. Okay, so we're actually going to get equivalently 3, -3. So I'm going to go 3 in the x direction, 1, 2, 3, -3 in the y direction. 1, 2, 3, 1, 2, 3. Okay, and here are 4 additional points on this line. We have -5, 10. We have -2, -2, 7. This is our original point, which is A. 4, 1. And we have 7, -2. Okay, now part C asks us, is either point Q or R on this line? Okay, so Q gives us -21, 23. What we want to do is we want to find this algebraically. Okay, so I'm going to take our parametric equations. So let's start with the x. So we're going to find if Q is on the line. So for x, our x is -21, and we have 1 minus 3t. What we're going to do is we are going to solve for the parameter t. Okay, so -21, move that 1 over, -1, and that's all going to be over -3. So that's -22 over 3. So in order for us to get -21 for an x value, our parameter would have to equal -22 over 3. And what we want to do with that is we can take one of two approaches. We can sub this into the parameter for y and see if we get 23, or we can solve for the parameter using the 23. So if we choose to solve for the parameter using the 23, 4 plus 3t, we'd bring that over. We'd have 23 minus 4 divided by 3. And I get 19 over 3 equals t. Because these parameters are different, therefore, Q does not lie on this line. Okay, we're going to do the same thing for the other point R. Okay, so we know that the coordinate is x, y, -29. So let's plug -29 where the x is. Okay, equals 1 minus 3t. Bring that 1 over, becomes -1, so it becomes -30 equals -3t. And we can just divide both sides by the -3. I get 10 equals t. That's a nice parameter. Now let's try 34 in here. 34 equals 4 plus 3t. Okay, bring that 4 over, it becomes -4. So we're doing 34 minus 4 over 3 equals t. Okay, so that's 30 over 3. I get 10 equals t. Okay, because the parameter is the same, that means that we could sub in 10 to this parameter and come out with this point. So yes, R is indeed on this line. So example 3, determine vector and parametric equations for the line containing the points E and F. Okay, so first what we want to do is we want to find a direction vector. So let's call direction vector M. It's actually going to be EF. Okay, so we're going to subtract the 6 minus -1, comma, and then the 11 minus 5. Okay, so I get 7, 6. So this is the direction vector. Okay, so pretty much right now, all we have to do is for the vector equations, we have to write one of the points. It doesn't matter if you choose E or F. I personally like F because they're whole numbers, or they're both positive numbers, I should say. Okay, so 6, 11. plus we want some parameter t, and then we want the direction vector. Okay, so we can write the vector equation like this, or the parametric equations, where we take 6 and 11, and we write them in the 6 pertaining to the x's, and the 11 pertaining to the y's, and then plus 7t or plus 6t. 7t for the x's, 6t for the y's. Okay, so there are the vector and parametric equations for this line. So in B, it asks us, what are the coordinates of the point where this line crosses the x-axis? Okay, so we know that when it crosses the x-axis, y equals 0, right? The x-intercept. So what I would do is I would take these parametric equations and I would sub in y equals 0. And then I would solve for the parameter. So in other words, what did we have to sub in as the parameter in order to get y as 0? Okay, and that's really, really ugly, but this is the answer. Negative 11 over 6 would have to be the parameter that we subbed in to get y equals 0. So since now we have t equals negative 11 over 6 as the parameter, what we have to do is we have to just simply sub that in to the x equation. So 6 plus 7 and then negative 11 over 6. Okay, so 6 minus 77 over 6. 6 minus 77 over 6. I get negative 41 over 6. So negative 41 over 6. Throw an equal sign there. Okay, so what are the coordinates of the point where the line crosses the x-axis? Okay, it's negative 41 over 6, comma 0. C, can the equation vector r equals negative 15 comma negative 7 plus t 14 over 3 comma 4, where the parameter t is an element of the real numbers, also represent the line containing points E and F? Okay, so first of all, what we want to do is we want to ensure that they have the same direction vector, okay, so that they're going at the same angle and pretty much like the same slope if you want to compare it to like the grade 9, the slope. Okay, so the direction vector in this new equation is 14 over 3 comma 4. Okay, are we able to multiply this by some constant in order to get 7 comma 6? So in order to get 7, we'd have to multiply this by 3 over 2, because then those 3's would cancel and then 14 would cancel with 2 to get a 7. Okay, so if we multiply this in, we do get that 7. What we're really checking for, because we made this a 7, what we're really checking for is that 3 over 2 times 4 equals 6. Well, 4 and the 2 cancel out to a 2, 3 and 3, 6. Okay, so therefore they both have the same direction vector because they're multiples of one another. Okay, so therefore same direction vector. Now, what we want to do is we want to ensure that negative 15 comma negative 7 lies on our line. If it lies on our line, then it's the same direction vector. We have a point, and then it's going to be the exact same line. Okay, 6 and 11 plus 7t plus 6t. Okay, so let's go ahead and plug in negative 15 to where that x is. So negative 15 equals 6 plus 7t. Bring that over. Negative 15 minus 6 over 7. Negative 21 over 7. I get t equals negative 3. Okay, let's do the same thing with the negative 7, but the negative 7 is in for the y. So negative 7 equals 11 plus 6t. Bring over that 11, negative 7 minus 11 over 6 is negative 18 over 6. And again, I get t equals negative 3. So because we can sub in the same parameter into our equation, get the point -15, -7, and the direction vector is the same, then yes, this is another way that we can represent the line containing points E and F. Example 4, determine a vector equation for the line that is perpendicular to this line and goes through the point P. Okay, so if we want a vector equation, we know that we need vector, we need a point. Well, that's easy. It says that it goes through the point 6, 5. And now all we need is a direction vector, and then we'll put T as an element of R. Okay, so for the direction vector, the information that we're given is that it's perpendicular to this direction vector, 4, 1. Sorry, I did that backwards. The direction vector is -3, 2. Okay, so I'm going to show you how to do this like the easy way. Just a little throwback for the slope. The slope of any line is, you know how we said that this is a comma b for the direction vector? The slope is actually b over a. So the slope of this line would be 2 over -3. This way we can do it easily. We know that the perpendicular slope is the negative reciprocal. So let's flip the 2 and the 3. So we get 3 over 2. And instead of it being a negative number, we're going to have it as a positive. So we can write this, because this is b over a, we can write it as 2, 3. Okay, so perpendicular, flip these around and flip the sign of one of them. And that is our vector equation for a line that's perpendicular.